Hello and welcome to the world of NDE 4.0. My name is Johannes Rana and today is a great day because today we will be talking about the working principle of phased array ultrasonics. Now, a couple of weeks ago, I did a video on the history of ultrasonic testing, and I will put a link to that video right here. Now, in that video, we talked about that ultrasonic testing, like we know it nowadays, was really developed during the Second World War. That right after the Second World War, the equipment became available to the public market. And that was kind of the birth of ultrasonics like we know it nowadays. Now, the development of phased array ultrasonics actually started in the same time. It started somewhere in 1954 with first experiments on phased array. And finally, in 1982, the Fraunhofer Institute for Non-Destructive Testing actually produced the first microcomputer-controlled phased array system, which really made phased array to what we are used to use it nowadays. It still took a couple of years until it became commercially available. And that was 1997. And you can see this system, this phased array ultrasonic system here on this slide. This was the first commercially available phased array system. Not really that handy, but already quite powerful actually. And it was called the Sapphire system. Now that system, or its newer version, actually is still available under the name Sapphire Quantum. Now, the company producing it was renamed a couple of times from Siemens to Intelligent to Areva, and currently it's sold by Framatome. Now, but this video is not about the history of phased array. This video is about, okay, how does phased array ultrasonic testing work? Now, in the last video I did, we talked about, okay, how does conventional ultrasonics work? We said, okay, we have an ultrasonic instrument. That ultrasonic instrument produces a strong pulse, which is then connected to a probe, and its active element is producing a short excitation, which is then traveling through the component, and if there is anything within that component, like a flaw or a back wall, then actually the wave is reflected and is traveling back to the transducer, is received by the same probe, and then depending on our time the signal needs to reach that indication and come back to the surface, actually we can calculate the depth of our indication. Now, actually, with phased array, it's about the very same. Now, the only thing what changes is if we have a phased array probe with, for example, here in this example, 8 elements, we actually not need one pulsar, we need 8 pulsars. If the phased array has 32, we need 32 pulsars. And we also need 32 receivers. Now what we do is, with each of those elements, we will fire, but we will have short delays between one of the other. And we can program those delays. So let's do an easy example. So let's say we first fire with that one element. A couple of microseconds later, we fire the second element, and so on and so on. And you can already see what is happening. We are creating an angle wave in our component without actually having to use a wedge. So what we can do with those delay times, we can actually create an angle wave, and we can control the angle we want to use. So this is application number 1. For sure, what we are producing here is a longitudinal wave. If we want to produce a shear wave in our component, we have to add a wedge. And if we add a wedge, then actually what we can do, we can control the angle of our shear wave in our component. Now, the second example I want to show you, in this case, we first fire the outermost 2 elements. Then we go inwards until we reach the middle. And what you can see, what happens is actually we are focusing. We are producing a focused wave. So this is actually our application number 2, our use case number 2 for our phased array. And for sure, we do not have to use all 8 elements. We can also use a subset of those 8 elements and create actually a smaller aperture with a bigger opening angle. Okay, so now we have those 3 use cases, and for sure, we can mix them. For example, we can use a limited aperture with some angle control and perhaps some focusing. Now, what we can also do is we can do some scanning. We can, for example, do a linear scan. So we put our probe on our component, and then we fire the first 4 elements. Then we wait some time for the wave to propagate and come back, and for all the remaining echoes to fade away. Then we fire again, but this time using the middle 4 elements, waiting again, and then actually using the last 4 elements. So we can scan a component without even moving the probe. And then perhaps we move the probe and then we do the same. We can do a similar thing for actually changing our angle. We can first have one focal law, one set of delay laws for one angle, then we have a second focal law and a third. And now what we can do, because now we have this one A scan from here, one A scan from the middle, and one A scan from the right, we can actually stitch them together and make a good image out of it. And this is all those sectorial scans you're used to use, you're used to look at. Now this here, I think this one has about 10 angles for sure. This one is a shear wave inspection. But what does it mean that we have 10 angles? Actually, this is 10 consecutive shots. And between one shot and the next, we have to wait a little bit, or the machine has to wait a little bit. And that's perhaps one thing I really need to mention in this video. If you use phased array, actually it's not you put your probe on there and you get this image. No, the instrument is doing 10 shots. And therefore you have to watch your pulse repetition frequency, because actually you cannot use an as high pulse repetition frequency as you're used to use it with a conventional setup. So in some cases where you need high inspection speeds, actually a conventional probe might be more useful than a phased array. And for sure, we can also do some scanning on the focusing plane. For example, we can do a close focusing, a not so close focusing, and a focusing to the natural focus. Now, this is perhaps also one thing I should be mentioning, is you can only focus in your near field. You cannot focus on anything in the far field. Okay, so now we talked about those 3 operation modes, and I think what you see is really a phased array probe is a multi-purpose probe. And it's really good if you have one probe with you, you can use it for all kinds of applications. But if you have a very dedicated task, in some cases it might be better just to use conventional probes and not to deal with all the settings of a phased array probe. And also a phased array probe, you have to imagine you have to contact all those elements. You need an instrument has all those wires, so all your equipment becomes more expensive. So in some cases, phased array might be the solution you're looking for, and in some cases, conventional might be way better. Up to the moment, we only spoke about 1D phased array probes. So with elements, positioned one right next to the other. You could also imagine doing actually a 2D phased array probe. So not only having the elements in one dimension, but in 2, in a grid. With that, for sure, what you can imagine is you can actually not only tilt your angle in one direction, but also in two. So you can do all kinds of things with that one. You can also do a way better focusing because you're not only focusing in one direction, but in two. You can also have it for a better aperture control and then move around your ultrasonic like you want to move it. However, if you think about having a 2D probe with 8 times 8 elements, this is already 64 channels. And if you think about 32 times 32, this is already more than 1,000 channels you need to have on your phased array instrument to actually control this. So it's a lot of electronics we need. Also, the transducers get a lot more expensive. And there is another issue. If you imagine you have to contact all those tiny elements, and then you need to add some backing on the back end of your probe, it is actually getting quite difficult and quite hard to produce. Therefore, those phased array probes, they cost a lot, number one. And number two, it's also, you do not get the power in your component as you used to get it from a probe with a similar, from a similar size. So for special application, a 2D phased array probe might be the one you want to use, but in most cases, a 1D or even, as we already talked about, a conventional probe could be way better. Now, there are also specialist probes like ones with round phased array elements and all kinds of others. But this is here about the basics. Now, thank you for watching this episode. If you have any comments, if you have any questions, feel free to ask them. Next time, we will get into automated ultrasonics. As usual, you will find more information in the description. I hope you liked this video. I hope you subscribe to this channel. I hope you give me a thumbs up for this video. I hope I will see you soon. So thank you for watching. See you soon. Thank you and bye.